Okay, hello everyone. Today's speaker is Selman Ipek from Cihan University. He's going to tell us about topological methods for studying contextuality and Bell inequalities. So Selman, floor is yours.
Okay, thank you very much. So I will just say briefly top methods and for studying contextuality and Bell inequalities. Okay, so I think that Aziz talked briefly about Bell inequalities. But I will just give a sort of geometric picture, which sort of follows from my talk a couple of weeks ago. So if I have some sort of, we think of this as maybe the polytope of simplicial distributions, something like this. Okay, yes. And then I can sort of, there are certain vertices. So if I think of this from there are certain simplicial distributions that are extremal, and some specific ones are the ones that are deterministic, that are in bijective correspondence with the outcome maps. So maybe just as a sort of illustration might be something like this. And the convex hull of these is going to be the Bell polytope. So this in our notation we will see is called C of X of Y. Okay. Just get my notes in front of me or something. Okay. Yeah, so this object here is what we're going to be calling the Bell polytope, non-contextually polytope. These will be more or less, you can think of them as like delta R's, sort of embedded in a real Euclidean space. And then we have that these sort of flat planes, these are the Bell facets or Bell facets slash inequalities. Oftentimes people are interested in knowing what these Bell inequalities are because Bell inequalities give a very straightforward way for telling whether a particular distribution, say I have a arbitrary distribution P, the inequalities give you an easy way to check whether that distribution is contextual or non-contextual, namely a P that satisfies all of these inequalities will be inside the blue region, and if it does not satisfy, therefore it must be outside of the blue region, and then we call it contextual. So, I mean, maybe a more sort of polytope, more within simplicial distributions, we have X, Y as a simplicial scenario. And then you have something like outcome maps. And then you actually have the simplicial distributions that come from those outcome maps, D, Y. So I will use the notation from the paper. So the set of deterministic, so these distributions, we'll call them deterministic because when you restrict them to a simplex, all the probabilities are always 0 or 1 for a particular outcome to occur. Of deterministic distributions is we use D list of X, Y. Later, we will restrict to Y being nerve of Z mod 2, and then we will just suppress the Y notation, but I will keep it explicit for now. So Aziz talked about this last time, or maybe even just in the first talk, there was this sort of natural map, which goes like this. So the set of non-contextual distributions, so the set of contextual distributions is going to be something like this. C of xy defined as being the image of this thing, which I can also write if I think of embedding these. Hold on, let me think. I can think of embedding these delta r's in some real Euclidean space, and then you have that it's like the convex hull of these things. And that this C of xy is precisely what we call, oops, no. This thing right here is just what we call the Bell polytope. So there's just a quick example. If you have a X, which is like the diamond, so say, I think that we need to number these 1, 2, 1 prime. Then what we have is that the outcomes that you can put, the outcome maps are going to be like, I can choose some outcome, a bit on one of the edges, and then a second edge, and then the bit on this third edge, the one face, is determined. If I pick another edge to assign a bit to, then I actually have that this one is determined now by this. So there's 3 possible distinct bits that I can put on these edges. So there's going to be 8 possible outcomes. So we have something like R goes from X to N, Z, 2, which is precisely, I will say something like this, A, B, C, and Z2, 3, in terms of bijective correspondence. And then you have this map delta, and then you get, so for each of these, you actually have, I will spare you guys basically I can think of there being 8 possible deterministic distributions. So the case where I have zeros everywhere, so A, B, and C are 0, maybe I will put them here, 0, 0, and 0, gives me a distribution like this. And then there are 8 like this. And then even further than that, this distribution here that I have written, I can think of this as being embedded in some Rn. So here I put an ordering on the coordinates, just some ordering. So then maybe it's like 1, 0, 0, 0 for the top simplex, and then 1, 0, 0, 0 for the second one, and so on. So then I can really think of these as points in Rn, and then I can really think of this definition of C of xy as really being like the convex hull of some delta r's. Now, maybe I should put quotations here, but something like that. Okay, so actually, Bell inequalities. So a couple of weeks back, I talked about polytopes. So I will just say I have a convex polytope in RD, and you have V of P are its extreme points. So what does it mean geometrically to be a facet, or how do people who come from the polytope perspective define a facet? So a facet F subset of P is an D minus 1 dimensional affine subspace of P such that F is equal to P intersection with some half space, or not a half space, rather, just a hyperplane D such that AX, or I will X equals B. So we say that, so this is going to be a face, it's like a subpolytope of P, and of course, oh, sorry, I should also say that this inequality, so we have that A dot Y greater than or equal to B for every Y in P. So you need the inequality to actually be valid. So all the points in P must satisfy it, or it's sort of like a trivial face kind of. Okay, so this is how you would have a face. So this is just the intersection of a hyperplane with the polytope. So this is, you can consider this to be this what I have here in the brackets to be the facet. And then you can also, so we don't actually, so it's kind of interesting. We don't actually use this picture very much in some of the stuff that we do. We never actually use the fact explicitly that, for example, a facet, another definition is that, so H is equal to X in RD such that A dot X equals B is a facet of P if and only if and only if there exists at least D affinely independent VI in V of P such that A dot VI equals B for every VI. So another way, so if you guys recall from 2 weeks ago, a vertex, so that's kind of like a dual notion. A point is a vertex if and only if it's tight, so it satisfies the inequalities with equality for at least D inequalities, and those inequalities have to be linearly independent. So here you have a sort of similar sort of dual notion. Something is a facet if you have, you know, D affinely independent vertices that saturate that facet. That means that they lie on that hyperplane. So then you have that H as a facet of P. So that's some more like, I guess, a algebraic description of the facets, maybe geometric. So then you have that, you know, the Bell inequalities are facets of the Bell polytope C of XY, which means, so maybe we just say that. You have that P is in XY if and only if P satisfies every Bell inequality. So what we kind of want to do here is it's a sort of open problem to find a lot of interesting Bell inequalities. This is sort of interesting from the physics point of view because, you know, for a given simplicial scenario, you might not be able to, it's a hard combinatorial problem to find all the Bell inequalities, but sometimes it's interesting to find a subset of the Bell inequalities because being able to have those, you can still show that certain quantum states or certain kinds of distributions are contextual. Sometimes these can be used for information processing tasks and things like that. So people in physics are interested in determining all the Bell inequalities, but even just a sort of interesting family of Bell inequalities is also useful. So our goal is to determine Bell inequalities for here. We will look at two-dimensional spaces with outcomes. So our outcome space in Z2 or just okay, so maybe just quickly, you know, there are some interesting families of scenarios within this sort of restricted case. So people may be familiar with the CHSH scenario. So that's something like this. So that falls within the purview of what we're looking at. Okay. Any questions so far? Okay. Okay, so I'm just going to recall some basic facts. Okay, so this is some basic facts about simplicial distributions. So we tend to think of this map here as an inclusion. So I know Aziz talked about this last time, but given some, I mean, I tend to think of this as an inclusion. We have the following sort of induced maps, which is F star goes from D. These are for general X and Y actually, but I will suppress the Y just out of laziness. We also have C of Z, sorry. Okay, and then Aziz mentioned this last time that we have this sort of nice relationship that if P in S dist of X is, I will just write NC for non-contextual, then P equals of P is non-contextual. So gluing, this is sort of one of our fundamental results. So I think that the basic scheme that we are trying to exploit here is, you know, what you might colloquially call like bootstrapping. You have some independent spaces that you understand well. Maybe you know two constituent subspaces A and B, and you know that they're non-contextual. What can you say about their union? So when you glue them along a certain subspace, along their intersection. So if you have X is equal to A union B and A intersection B is a simplex, and here and okay, yeah, I think it still works. Then P in S X is contextual if both P, A, and S. Okay, so basically, so if you have a joint space A union B that's glued along a simplex, then a distribution on X is non-contextual if and only if the restrictions to A and B are also non-contextual. So there's some very examples. These are the classical n-disks. So, for example, we know that a simplex is classical, non-contextual, and if I glue another two simplex along a common face, this edge right here, which is also a two simplex, or sorry, it's just an edge, then you have that this is also classical or non-contextual. So this thing, we will call this a four disk, and we parameterize these by the number of edges on the boundary. So another example would be you have this. If you iterate, you have this piece is also. So now you've maybe glued the previous space along a new two simplex with a new two simplex. This is a five disk, so on and so forth. So you can keep iterating this, and I will not give a formal definition, but you just sort of like you just keep gluing triangles. So you sort of see the pattern. I will maybe do one more. So this is a 6, I think. 1, 2, 5, 6. Yeah. This is a 6 disk. So the other thing that Aziz talked about last time was the notion of extension. So which is something like this. So if you're given that F and so if you're given a map like this, maybe an injection or inclusions rather, and some surjections such as C of Z, as well as then we have that P is non-contextual. lattice P tilde in so I think an example makes this one pretty easy to see what's going on, and it's relevant to the kinds of spaces and examples we'll be looking at. So suppose that you have I guess this would be a horn. So you have like a 3 simplex, but the bottom face is not filled in. So I will make it just red like this to indicate that this one is not in. So what is this extension telling us? It's telling us that we have f z to x, and then so let me give you the other space, which is just the boundary of delta 3. Like this. So all the faces are included. So this is, what is this, like delta 3, 1, whatever. I know that there's some notation for this. This is boundary of delta 3. And then, so when we look at this, we see that the outcome maps are determined by triples of bits. So if I choose an A, B, C here, it determines all the other outcomes on the other edges. And the same thing also holds true for this. So you have that the first condition here is satisfied. You have that C of X and CZ are going to be surjections. In fact, they're just bijections in this case. And if you assume that X is, in this case, this means that it's the scenario X is non-contextual if you say that this is surjective. And so we independently proved in the paper somewhere, just through a computation, that the boundary of delta 3 is in fact non-contextual. So that's the second sort of ingredient there. And we see that there is a sort of mapping of, there's an inclusion in here. So then we have that the extension lemma says, in fact, that P in here can be extended to P tilde here. And this actually happens if and only if a certain set of inequalities happen, called 3 circle inequalities. And it has to do precisely with the probabilities associated with these right here. Maybe that's not such a good color. So what do I want to say about this? I think that that's more or less what I wanted to say, that P is non-contextual if and only if it extends to some P tilde in the boundary of delta 3. And it turns out, in fact, that you can show that this extension occurs if and only if certain inequalities are holding. So that's sort of the basic scheme that we were looking for. You have that you have a basic space that you're interested in looking at. You have a space, a target space that you know is non-contextual, and then you try to show that there's an extension and that this extension is possible if and only if some inequalities hold. That's the basic scheme. Okay, so let's slightly shift directions to sort of understand where these inequalities are coming from. So I want to speak briefly about a sort of special set of coordinates that we can use when we have two-dimensional is y equals mz2. So we have that there's this sort of picture that we have a two simplex, and inside it, maybe we place some probabilities for sigma, and we know that P sigma AB must be non-negative, and that AB P sigma AB equals to 1. So there's another way to, so here you see that we have 4 probabilities subject to some constraints. So in fact, we can avoid dealing with these constraints at all if we just use the marginal probabilities. So what do I mean by that? Consider we have these faces. So maybe D0, D2, D1. And we have, so maybe I will call this thing P tau 0. And this will be B. P tau 2A. P tau 1A plus B. So these are the marginal distributions. We know how to find the faces. So it turns out that you can just express these probabilities directly using the marginals instead. So I'll illustrate this for just a single case very quickly. So P tau 0, and I will take the 0th. So of course, it suffices because we're working in Z2. If I know P tau I of 0, then P tau I of 1, the other possible outcome, is just given by 1 minus. So it suffices to look at the 0 coordinate. So here, plus P tau 1, 0 plus P tau 2, 0 is equal to. So if you recall what these look like, what it is P sigma 0, 0 plus P sigma 0, 1 for the first one, plus, hold on, did I do it the other way around? Yeah, I should do P1. Yes, like this. P sigma 0, 0 plus P sigma 1, 1 plus P sigma 0, 0 plus P sigma 0, 1. So when you sort of just trivially add this up, you have P tau plus P tau 2, 0 equals 3 times P sigma 0, 0 plus P sigma 0, 1 plus P 1, 1. Okay, so I know this seems a little bit trivial, but just showing you that essentially you can solve this because these pieces here and one term from here, those just add up to 1, and you get that P sigma 0, 0 is equal to 1/2 P tau 0, 0 plus P tau 1, 0 plus P tau 2, 0 minus 1. You can generalize this just for the other outcomes. So in general, it will look like this. P sigma AB equals 1/2 P sigma, PT0 PT2A plus PT0B minus PT1A plus B. And now the only thing we need to do, because these marginals are just probabilities between 0 and 1, it could be the case that I could choose some values between 0 and 1 such that this would not be non-negative. So I do have to enforce the non-negativity condition. So, but you have a general formula. If once you know, if you can just parameterize any of these bulk interior probabilities by just the ones on the boundary of the simplex. Okay, so then we have so more or less what the following result is going to say is that I can think of two-dimensional simplicial distributions just in terms of tuples of marginal probabilities that satisfy certain inequalities is what this next sort of set of results that I want to say is. So if X is generated by two simplices, sigma 1, sigma n, such that each delta sigma I does not contain edges. The map phi to is convex. Convex. Okay, so let's just unpack this real quick. All that we're saying is that if you have a two-dimensional simplicial set generated in this particularly nice fashion, then we can think of the set of simplicial distributions, which is a convex set. In fact, it's a polytope, but using the sort of natural embedding, using these probability coordinates, the ambient dimension could be different. So there's something, what are we doing? Essentially, we're defining this map. We're thinking of and this map is convex and injective. So if this set is convex polytope, then the image is also going to be a convex polytope. And how can we think of this more precisely? In the simplicial distribution can be given by p tau 0. So we're just keeping the 0 coordinate, and tau x1 0. These are the non-degenerate edges in our two-dimensional simplicial set. So that's what this means. And so we can think of this as being embedded in R to the number of non-degenerate edges. So we, in fact, we'll define this image as just P of X, which is a subset of R x1, 0. So X rotation coordinates. Some of the calculations are a little bit cleaner using a slightly shifted and scaled set of coordinates. So I'm just going to say take some edge, non-degenerate edge in my simplicial set. I'm going to define its expectation value as being the normal expectation value that we know from probability and statistics. So it's like a weighted It's just a weighted average, which is p tau 0 minus p tau 1, something like this. Conversely, p tau 0 is like 1/2. I think it's 1 plus tau bar. Basically, you see that there's just a sort of very easy relationship between the two. But what's sort of nice in this case, if you look above our expression here for, you have 3 probabilities, but sometimes the constant term is -1, sometimes it's +1. It's a little bit sort of a complicated formula. So when you use expectation coordinates, P sigma AB are just given by 1/4, 1 plus, so the constant term is always the same, -1 tau 0 bar. I think this is actually incorrect. A tau 2 bar plus -1, A plus B tau 1 bar plus 1, B tau 0 bar. And again, non-negative. So then it's sort of easy to define Px as the intersection of finitely many half-space inequalities are x1, 0, a dot x greater than or equal to -1. This is a vector of some number mx of -1s, basically just because you're taking this one and bringing it over to the right-hand side. And here we have that there's a specific formula for A. Essentially, we're just trying to reproduce these inequalities for every simplex. So you just have that A is a real matrix mx cross dx here. Mx is equal to x2, 0 cross z2, 2. Okay, so what is this? Basically, I'm counting the number of probabilities in my two-dimensional space. So if I have a picture like this one, then there's going to be 4. But then, you know, in something like this, for every simplex, I have 4 possible probabilities. That's all this is doing. It's just counting that. And then you have Tx is equal to the number of non-degenerate edges. And the formula for this thing is exactly as you might expect for it. So, or I will put this later. So the coefficients are either -1 to the A if my edge is equal to the 2 face of sigma, -1 A plus B if tau is equal to D1 sigma, it's -1 B if tau is equal to D0 sigma and 0 otherwise. Some just facts you can get from this is that P of X is full dimensional in X1, 0. And then, so for the next talk, the one will also be about two-dimensional spaces. So let me add a couple of additional sort of definitions or terminology that we tend to use. So let's, I want to think of I as being a one of the elements from 1 to mx. So I'm just ordering, so I want to think of ordering my two simplices and the outcomes in a particular way so that it maps to I like this. It'll just make my life a little bit easier. So we say that a simplicial distribution is tight at an inequality if you have that. So let xp be equal to phi of p, or you can just call it x, then we say x is tight at an inequality if ai times x is equal to -1. So that means it satisfies the inequality with equality. So you also can define the set of such inequalities like this. I in x such that ai x equals -1. Okay, yeah, that sounds good. And then also we say that the rank of a simplicial distribution is equal to the rank of a matrix A Z X, where what I mean by this notation is that I'm only taking the rows of A such that the index I is there. So we say that the rank of a simplicial distribution is the rank of the corresponding matrix given like this. And then so from last time, we then have that P in S ist of X is a vertex if and only if rank of P equals just actually x1, 0. So this will come in, this notion will come in handy when we deal with twisted distributions. These coefficients are a little bit different in the sense that we will have that this will be twisted, so to speak, by some value beta. But otherwise, the polytope will look quite similar, and the sort of way everything is defined is very similar. The only difference will just be that some of the one faces will be twisted in this particular way, which is something that happens naturally for distributions coming from quantum mechanics. Sort of very important, no, well, it's very common notion in polytope theory is this Fourier-Motzkin elimination. It's kind of just the analog of Gaussian elimination for inequalities. So if I have a set of inequalities, let's say X, B1, and then, am dot X BM, and I want to eliminate a variable from this set, say one of the variables, say xj, then I will sort of split these up into two pieces. I will look at xj being less than or equal to some linear expression, k not equal to j, alpha k, let's say 1, 2 of xk. So I'm just rearranging these things. So I have to split them up into two different cases. Xj less than a linear expression in xj greater than. So there can be some perhaps number lambda minus of these, and then xj greater than or equal to, say, some k prime not equal to j, beta k prime 1 x k prime. Let's say there's lambda plus of these. So what happens is the way that I eliminate these, if it was Gaussian elimination, I would, not really need to do this. You just solve for xj, and then, you set the expressions equal to one another. But here it doesn't quite work like that. So you have to, so the initial set of inequalities is valid if and only if I basically have to pair each inequality that I have here with an inequality here. So in particular, I have that this expression is less than xj, and this expression is greater than or equal to xj, then naturally I have for every expression showing up here, it must be less than or equal to an alpha k expression up here. So then you have stuff like this showing up, k prime not equal to j, beta k prime, and say this is L, the Lth one, x k prime less than or equal to some k not equal to j, alpha k L prime. Oh, maybe I'll make this prime. Okay, so, and then you have how many of these? Well, you have to pair every lambda minus with a lambda plus. So there's lambda plus times lambda minus inequalities. So this is sort of more or less the general case, but for our purposes, it will not need to be quite like this. So we're very lucky in that our xj's, the a values that we have here are either plus or minus 1 or 0. So it will actually be suffice to, if you want to eliminate a variable, it suffices to just add the inequalities. And since they're all always in this form, it'll suffice to add inequalities where the variable we want to eliminate is positive with one that is negative, and there won't need to be any sort of rearranging of stuff otherwise. So let me give you an example. So if I have this diamond, so let's call this T2, T0, T1 equals T1 prime, T2 prime, T0 prime. Then we have a set of inequalities. I will take, for example, just the one where everything is well, I'll just take some representative examples. In fact, there's 8 inequalities, 4 coming from here, another 4 coming from here. I will not write all of them. It's possible to write a simple expression, but it won't be very useful, I think. So I have one inequality perhaps like this, T1 plus T0, tau 0, greater than or equal to -1, and then tau 2 prime minus tau 1, which is the same tau 1 plus, minus tau 0 prime greater than or equal to -1. I can just add these expressions together, and I get that tau 2 bar plus tau 0 bar plus tau 2 prime minus tau 0 prime greater than or equal to -2. This turns out to be a CHSH type of inequality. It's got a very similar sort of structure for people who are familiar with those. So geometrically, we sort of interpret this as you you got rid of an edge when you did the Fourier-Motzkin elimination, because you removed precisely the edge that's interior to both, and now you just have inequalities that will depend on the boundary edges. Any questions so far? I went through in some more depth than necessary because I think that that would be more useful for next week, or one of the subsequent weeks. So then we have an circle inequalities. Okay, so it will be easiest to just show that we can generalize this notion. So if I have some classical n-disk, perhaps like this one. One moment. Oh, yeah, I did it wrong. Sorry. Here it is. So if you do the same thing and you perform Fourier-Motzkin elimination on the interior edges, you will get some inequalities just depending on the boundary. In fact, you can, if you start from a classical n-disk, then you always get something that looks like this after you end. N minus 2 plus some I equals 1 to n. So say in this example, we had, tau 1, tau 2, tau 3, tau 4, tau 5 in this case. You have -1, AI, these are bits, Ti bar, where we have the restriction on these AIs that AI equals n plus 1 mod 2. So I will just define it like this. The n-circle inequalities are precisely what you get from taking a classical n-disk and performing that Fourier-Motzkin elimination. So let's see. So okay, so there's a sort of interesting inverse thing that happens about with the extension. So if you have that a classical n-disk is denoted dn, let be classical n-disk. We have that a distribution P on the boundary extends to P tilde in S dist dn if and only if the n-circle set inequalities and some of these statements are modulo some trivial inequalities. Sometimes when you do the Fourier-Motzkin elimination, it just tells you that the variables are precisely between the bounds that you expect, which, by the way, I realize now I did not mention this. When I define this T bar, it is between -1 and 1, whereas the marginal probabilities are, of course, between 0 and 1. But when I say trivial inequalities, it just means that you end up having the marginal probabilities being between 0 and 1, or the expectations between -1 and 1. So some of these statements are always just modulo, satisfies n-circle inequalities and trivial things like that. So we also have the sort of addendum to that, which is if I have like these other sorts of situations where suppose I have a sort of boundary of some x, and x is precisely a gluing of something like this. Basically, it doesn't have to be this particular space, but it's like if I have a bunch of classical n disks and they're glued along a common edge, like this one. So in this case, I have three disks and they're glued along the pink edge. Then I have that the boundary, sorry, extends, and this happens if and only if n circle inequalities are satisfied. And that is all n circle inequalities have to be satisfied. So like this one, and this one, and this one, you know, all of them. And then it will extend. Okay. Couple more things. So I didn't talk about the cone. A lot of the spaces that we will be looking at can be thought of as one-dimensional simplicial sets that get coned off. So the definition is not strictly for one-dimensional things, obviously, but so if I have something like this, then its cone, which I try to make a curly C. So if this is x, then the cone of x is basically I'm bumping all my simplices up a dimension. So I add a cone point, and then so if I go from a one-dimensional simplicial set to a two-dimensional, so this is C of x. So those triangles are filled in, for example. So I want to say the following: if for some simplicial distribution we have that it's non-contextual, then the well, I didn't write what simplicial distribution of what of C of x, where x is a simplicial set, is non-contextual, then the restriction to the restriction P Cn to a circle Cnx is satisfies okay, so in particular, you can sort of, the canonical example is something like this. So if I have a distribution on this thing, which includes the four, so this is the CHS-SH scenario. So these triangles are filled in. If I have a distribution on this scenario, and you know that it's non-contextual, then the restriction to any n circle on X will also be it will satisfy the corresponding n circle inequality. So which we know exactly what that is. So if you have one direction essentially of what we kind of want to prove, which I will give an overview in a second. So if you have a certain sort of family of scenarios, these that are coned off from like simple circles, then we kind of end up wanting to prove that a distribution on this scenario is non-contextual if and only if it satisfies the n circle inequalities. So this is one direction of that. So let's make our goal a little bit more precise. Cn circle. So this is a one-dimensional simplicial set. That's a circle. So n will correspond to the number of edges. Cn. We can think of Cn tilde as the cone of this. So just as in the example above, what we want to show is that P in S dist Cn is non-contextual if and only if P restricted to Cn and circle inequalities. Well, in fact, I wrote this as goal, but this is precisely the proposition that we kind of want to prove. Let me make sure that I set everything the same way. Yeah. Okay, so let's get into how this sort of thing is proved. Any questions so far? I will give. Well, this example, unfortunately, is not illustrative of how it works in general. There's a sort of inductive step, but so sort of the original proof that we had in sort of, I guess, okay. So this is, I will just write it as simplicial contextuality. This is published in archive or in 2022, I guess, but maybe in Quantum in 2023, something like this. So the idea is as follows. So for the CHSH scenario, I'm giving this version first because the more general case is a little bit trickier to explain in full generality, but the basic concept is very similar. So if I have C4, which is something like this, so I have a bunch of different possible spaces. I've got C4. I've got, this is D4. I have C4 tilde, which is here, this is the cone point C. And then, so the n circle inequality that we're going to be interested in is precisely this thing, which is going to be corresponding to this, which it also shows up here. And then you have this other space, which is something like, let's see if I can draw it. If you see what's going on is that you have the, I will maybe just make this to illustrate the point. This is supposed to be the same exact four edges. Looks a little bit weird because I drew it at an angle. And I forget what we used to call this, but the idea is as follows, that this thing, which I will call just maybe Q or something, is actually the union of two boundaries of delta 3 glued along a 2 simplex. Maybe use this. Boundary of delta 3. And so I mentioned previously that the boundary of delta 3 is non-contextual when we deal with Z mod 2. So kind of what ends up happening is we know one direction of the thing that we want to prove, which is if P on this is non-contextual, we know that it satisfies these inequalities. So to prove the other direction, we want to use an extension kind of argument. So suppose that P satisfies the inequalities. We want to show that it extends to a certain space. That space is non-contextual. Therefore, it shows that our original distribution is non-contextual. And so just in broad strokes, for this case, what ends up happening is you use the gluing lemma because boundary of delta 3 is non-contextual, and you're gluing along a simplex. Therefore, by one of the basic results we mentioned before, we have that this space Q is non-contextual. And what you can show is that the fact that you satisfy these inequalities means that P here can extend to some P on here, and therefore non-contextual. Now, the sort of more general argument, so this is just an example, and this is not even quite the same argument as the one used in the topological methods paper. It's a little bit more involved. So let's, or at least I will try and demonstrate the spaces that are involved and sort of illustrate the point. So we introduce a space Z, which is a subspace of all the spaces that we are going to end up being interested in. Something like this. W is like if you sort of filled that in a sort of natural way so that you have a gluing of classical disks. So you have a two simplex, and then a classical disk. And I have to fill in. Yeah, so we have a disk like this. V, you kind of can see V in a couple of different ways. So you can see V as take the cone of a cycle scenario or of a n circle, glue it along Z with W. And so there's, I can just draw the picture, which is, let's see if I will be able to do it justice. So I just drew the W part, and then I will maybe add the extra lines in like this. So okay, so and then there's another decomposition of V that we will look at later. So this is L along M of R. And in this case, we have L is going to be the boundary of delta 3. It's L. You have M, which is delta 2. And then you have R, which is going to be very related to, I guess, the cycle scenario. I have the bottoms filled in here. This is R. Okay, so the essential argument is something like this. If you say that, so we already have one direction, that remains the same. you say that a distribution on, let me find myself. Okay, yeah, that's what it was. So we have that, we want to assume that P in S dist of Cn satisfies n circle qualities. What that means is that you essentially are able to satisfy, because Z is a subspace of Zn, you actually have that P restricted to Z satisfies all the n circle inequalities, and therefore you can have that P restricted to Z extends to W. You also have that, let's see, Q is a distribution on, let's see if I remember how this goes. Q is a distribution on, so we also have Q is a distribution on W, and capital P is a distribution on V. So you know that there is a, and I will sort of argue this in a second, there exists a P such that P restricted to Cn tilde equals P, and P restricted to W equals Q. And that essentially follows because we know that little p is satisfying the n circle inequalities. It extends to W. W is a subspace of V, and Q and P. So those can be made to match. So then we have, okay, this part is also, I must say this proof, I forgot how tricky it was. There's another space R tilde, which is like this piece, but without the bottoms. And you can see that this thing is actually a Cn minus 1 scenario. So sort of what you end up wanting to prove is that if you have some Q in of L, UM, R tilde, then Q is non-contextual. R tilde, only if Q restricted to, oh yeah, if only if Q restricted to R tilde is, so this is coming from the following piece. So I have a distribution on L, U, and R tilde. So that is like this picture right here, but without the bottoms filled in. So essentially what you're trying to do is you are noticing that I have this delta 2, and I have a boundary of delta 3 glued to that delta 2, and then you have this other cycle scenario on the other hand side of it. So because of the gluing lemma, and because I know that this is already non-contextual, I know that this distribution Q is non-contextual if and only if the restriction on the other side is now non-contextual. And then so you sort of iterate this process, and then you solve it for sort of like the simplest case, where we know that you end up reducing to another boundary of delta 3 on the other side, which is non-contextual, and then it sort of proves the result. It is a little bit involved in terms of the number of spaces, but that's the sort of idea. You sort of keep breaking it down, and then you do induction, and eventually you are able to prove that once you have the n circles inequalities satisfied, you have that the distribution is non-contextual. So that is what's called Fine's theorem. Fine first did this for the example I showed here. For the CHSH scenario, we did it in a more topological fashion. People have proved this in various ways. And then we proved it for the cycle scenarios. And actually, we go beyond this in the paper, but I think that this is probably suffices for now. Sorry, that last part I know was a little bit tricky, but to be honest, I think I forgot how tricky that proof was. Every time I look at it, it's like it's like I realize that it's quite tricky. Questions?
Oh, okay. Yeah. So thank you, Salman. So yeah, I agree that the proof is tricky. Yeah.
Thank you, Selman. Thank you.
Yeah, so I think what happens is our proof of Fine's theorem in the simplicial contextuality paper goes in a particular way. This does not quite follow that pattern, but in my head, that's always the pattern that I want to follow, was the one from that original anyway. So it's
yeah. I mean, I think it suffices for this talk to focus on the Fine's theorem version that's in the special quantum contextuality paper, but yeah, so we can actually extend it to cycle scenarios. Similar techniques.
Yeah, similar techniques.
Any questions from the audience? Any comments? Okay, so if not, let's thank Salman again.
Thank you, Selman.